All right, so let's talk about the relationship between position, velocity, speed, and acceleration, because they're all related kind of using calculus, and it'd be really cool if we could do problems that involve all four of these. Suppose that s equals f of t is a position function. So anytime we use that variable s, you can assume that we're talking about a position function. I think that's a fairly safe assumption to make. The velocity at time t, so remember that velocity, well, that's just the rate of change of position. So the velocity is the derivative of the position function ds over dt, which is f prime of t. These two are really saying the same thing. It's the derivative of s with respect to t, or f prime of t. You just pick your favorite notation. So the velocity is simply just the derivative of your position function. Speed is a little bit different. It's related to velocity, but in a slightly different way. When we talk about the speed cannot be negative. Velocity, on the other hand, can be negative. So when we talk about speed at time t is just the absolute value of velocity, or the absolute value of the derivative of your position function. So speed is just how fast are you going, regardless of what direction you're going. But velocity is a little bit more descriptive. Velocity is speed with direction. Because when you have a positive velocity, that tells me, okay, it tells me exactly how fast I'm going, and it tells me I'm moving in the positive direction. Whether that's up or to the right, or however the problem defines it. But I'm moving in a positive direction if I have a positive velocity. My velocity is negative, and tells me again how fast I'm going, but again it tells me now that I'm moving in the negative direction. So velocity I think is a little bit more descriptive. Speed just tells you how fast you're going, regardless of what direction you're going. Last thing I want to talk about here before we hop into our example is acceleration. Well, acceleration is how fast you speed up. It's how fast you gain speed. In other words, it's the rate of change of the velocity. Well, shoot, okay, the acceleration is the rate of change of velocity, so another way I can think about that is the derivative of velocity. Well, that's just the second derivative of your position function, d squared s over dt squared, or f double prime of t. So when we're working with f of t here, f of t, this is going to refer to a position function. So sometimes we might even just say height. F prime of t, the first derivative, this talks about velocity. The absolute value of that first derivative, that tells us speed. And the second derivative, f double prime of t, that tells us acceleration. So this is going to be a really handy thing to know. This is something I would absolutely have memorized, because we're going to be using them a lot in this section. So let's look at an example. Here I have f of t equals 18t minus 3t squared from 0 less than or equal to t less than or equal to 8. This is just describing the domain of your function. So it's not going to be all that important. Really, it kind of gives us a window to look at. I'm only looking at t values between 0 and 8. So part A, I want to graph this position function. So what do I know about this? Well, highest power is 2, so it's a quadratic. I know it's a parabola. And the leading term is negative. So, okay, it's a parabola that opens downward. It looks something like this. So at least I have a rough idea of what this looks like. I think I can be a little bit more specific. We can talk about maybe the vertex, or I think if we can figure out where it crosses the x-axis, that would be very helpful. Because right now, all I want is a rough sketch. It doesn't need to be super detailed. I want a rough idea of what this function looks like. So I'm going to find the x-intercepts, which means I'm going to take my function 18t minus 3t squared, set it equal to 0, let's solve for t. So let's see, I can factor out 3t, and that will leave me with 6 minus t is equal to 0. taking each of these and setting them equal to 0 will give me t equals 0 and t equals 6, which means it crosses the x-axis at these t values. So if I were to sketch out what this looks like, let's see if I can do that. So let's see, 1, 2, 3, 4, 5, 6, and 7, 8. So really, I'm not going to look past 8. I'm going to stop my graph right there. And actually, let's erase it because I don't want to get confused by it. So okay, we said it crosses the t-axis, or in this case the x-axis, at 0 and at 6 at these 2 points. Okay, if it crosses between those two, I can say a few more things. I can actually talk about the vertex. I know it opens downward, so that means the vertex, the highest point, has to be exactly halfway between these two. So right here at 3. So I know my vertex is, let's say, right around there. I'm going to make a rough sketch. Not going to be perfect by any means, and I can do better than that. Let's see. That's pretty good. That's what my position function looks like. So this blue parabola, that is my position function, which is S. Or here, let's call that F. Let's call that F of t. And actually, let's erase this part right here so that we're not totally moving into the next problem. So again, all I want is kind of a rough sketch. I want an idea of how this function behaves. I don't need to get too far into the details, just a rough idea of what this function's doing. Part B says find and graph the velocity function. Okay, let's just start right there. Find the velocity function. We said, hey, the velocity function, that's just the derivative of your position function. So the velocity function, if I want the velocity function v, that's really just the first derivative of my position function. So that's going to be 18 minus 6t. So okay, I found the the velocity function. Now I need to graph it. So I could graph it. I do want to be a little bit more careful about this, but again, I can hopefully gain a rough idea of what's happening. This is the equation of a line, and I know that this line has a positive y-intercept, so maybe maybe my y-intercept is somewhere up here, and I know that my slope is negative. So, okay, I know I have a positive y-intercept, a negative slope. Let's be a little bit more careful, though, and I'm kind of looking ahead here at this point when I think about how I'm going to approach this. It says, when is the object stationary, when is it moving to the right, when is it moving to the left? And in particular, I'm going to look at this guy. When is the object stationary? Because this part right here is saying, when is the velocity equal to 0? And I think that would help with my graph, too. So I'm just, first of all, going to take my velocity function, which I just found, 18 minus 6t, and set it equal to 0. So we can solve this equation pretty quickly. We'll have 18 equals 6t. It crosses at t equals 3. So let's say, okay, we've got a positive y-intercept somewhere up here, and then we cross right here at t equals 3. And then, okay, line just passes through those 2 points. Oops, that's not great. Let's see if I can do a little bit better. I think that gets an idea. It's still kind of a curve. That's about as good as we're going to get. Oops, don't need that part. So this red line that I've drawn, this is my velocity function. So this is v equals f prime of t. And one thing I really want to draw your attention to, hey, at t equals 3, we said the velocity was equal to 0, and that's exactly what's happening right here. The velocity is crossing the x-axis, or in this case, the t-axis right there. But remember, this is the derivative of position function. What's going on with position? Position, look at that. I've got a horizontal tangent line, which that makes sense. The horizontal tangent line, that's where I have a slope of 0. Slope of the tangent line is given by the derivative, so that's a pretty cool relationship that we just noticed. So, okay, we have our graph. So now, when is the object stationary? When is it moving to the right? When is it moving to the left? So let's talk about when is it stationary. It's stationary, stationary when the velocity is 0. That's what we said. We said when the velocity is equal to 0. Well, the velocity is 0 when t equals 3. So at this point right here, at t equals 3, that's when my object is stationary, at t equals 3 seconds. Now we got to talk about, okay, when is it moving to the right and when is it moving to the left? When it's moving to the right, what I'm really thinking about here is my velocity is positive. So in other words, my velocity should be greater than 0. So I want to look at the velocity graph that I've drawn here, figure out where my velocity is greater than 0. Where is my velocity positive? Well, in this section right here, my velocity is above the x-axis. I have a positive y value for my velocity. So my velocity is positive there, which means I'm moving in a positive direction. I'll assume that the positive direction is to the right this time. So, okay, what are the t values that I've highlighted on my graph here? So it starts at, in here, let's just be specific here, 0, and it goes to 3. So now we just need to decide, is the velocity positive at 0 and at 3? Well, here at 0, I have a positive y value, so yes, my velocity is positive there. So the way I'm going to show that 0 is included, that my velocity is positive, is I'm going to use a bracket to show that yes, that number is included in my set. That number is included in my interval. 3, however, the velocity is not positive there. It's 0. And I can actually look, we said it's stationary. It can't be stationary and moving to the right at t equals 3 seconds. It's got to be one or the other. So the way I'm going to show that 3 is not included in this interval is I'm going to use parentheses. That shows me that I want all of the numbers between 0 and 3, including 0, that's what this part says, but not including 3. Moving to the left, here in this case we're looking, okay, where's my velocity negative? Whoops, let's get rid of that highlight. Where's my velocity negative? Well, if it's not between 0 and 3, if it's not at 3, it's probably after. And I can look at my graph and I can say, okay, after 3, my velocity graph has a negative y value. So that if my velocity is negative, it's moving in the negative direction, which I'm going to assume is to the left here. So it's moving to the left from 3 to, I need an ending point, and for that I'm going to look at my domain. We said just to 8, so we'll say 3 to 8. Again, 3 is not included in this set. 3 is not included in this set because it's stationary at 3. Same reason, right? If I look at this point right here, it's not positive, it's not negative. So, okay, it's not included in this set. But what about 8? My point for 8, if I had to guess, would be like way down here somewhere. That certainly has a negative y value. So, okay, that means 8 is included in the set because I have a negative velocity at 8. So the way I include that is I use a square bracket. So here is my answer. It's stationary at t equals 3. It's moving to the right on 0 to 3, 0 included. And it's moving to the left on 3 to 8, 8 included. Part C says determine the velocity and the acceleration of the object when t equals 1. So this one's not too bad because we already have the velocity function. So the velocity function is f prime of t. So essentially I'm just going to take 1 and plug it into my velocity function to start off. So f prime of 1, we'll say, how about v of 1 equals f prime of 1 is equal to 18 minus 6 times 1. This is 18 minus 6. This gives me 12. Again, I want to give a unit here because we're talking about velocity. This is really 12. I guess we don't have a unit here, so I'm going to say meters per second just because I'd like to pretend that I live in a world where we all use the metric system. So we'll say 12 meters per second. That's my velocity. We don't have the acceleration function yet, so let's go and find it. Remember, the velocity, or excuse me, the acceleration is just the derivative of velocity, which is the second derivative of the position function, f double prime of t. So okay, I'm going to look at my velocity function, which is this guy right here. I'll go ahead and highlight it. 18 minus 6t. Derivative, the acceleration function, which is f double prime of t, that's equal to negative 6. Because 18 is a constant, that drops off. Negative 6t, that just becomes negative 6 using our power rule. And if I want to determine the acceleration at t equals 1, I'm just going to plug 1 into that function. A of 1 or f double prime of 1. Nowhere to plug it in. It's a constant function, is negative 6. I'd like to give a unit here as well. So because we said our units for velocity was meters per second, here, this describes the rate of change of the velocity. So sometimes we'll write this as meters per second, because what this says is my velocity is decreasing by 6 meters per second every second. So every second my velocity is going down by 6 meters per second. The other way we might write that, probably more commonly, we'll probably write that as 6 meters per second squared is probably how we would more commonly see that written. So there is my acceleration at 1 second. Part D, determine the acceleration of the object when its velocity is 0. Here, this is kind of a silly question to ask because we said, hey, the acceleration is the second derivative of the position function, which is negative 6. So earlier we found the velocity is 0 at t equals 3 seconds. So I'm going to take 3 and plug this into my function. A of 3 is f double prime of 3, which is still just negative 6 because it's a constant function. So we'll say negative 6 meters per second squared. Last part of this, we've talked about position, we've talked about velocity, we talked about acceleration. Let's talk about speed next. On what intervals is the speed increasing? So let's go back up. Remember that the relationship between speed and velocity, here I have, let's highlight it. If f prime is velocity, absolute value of f prime is the speed, right? We just said if it's positive velocity. Just take your velocity, make it positive, then you've got speed. So let's look at our graph here. And I'm going to look at my red velocity function here. I'm going to draw the speed function in black. So if your velocity function is positive, your speed function agrees with your velocity function, meaning it has the same value. So over here on this part, since my velocity was already positive, my speed is also positive. So the black line will fall right on top of that red line. If my velocity is negative, like it is over here, my speed should be positive there. So what's going to happen is this part of my graph is going to reflect across the x-axis. Sort of going to bounce off of the x-axis. So rather than going down, speed's going to go up. So this black line that I've drawn here, this is, I'll say speed equals the absolute value of f prime of t. So we've got speed, and we've got our graph. And what I'd like to do is I'd kind of just like to think about what the speed's doing on each section here. I kind of see two parts to my speed graph. First one I see is this right here. What's going on there? What's happening to my speed over time? So my speed starts off positive over here. It ends up at 0, and in between it's just getting closer and closer to 0. If my speed is getting closer and closer to 0, if my speed is 0, I'm stopped. Sounds like I'm slowing down. If I start off with a positive speed, end up at 0. I must be slowing down. That's not what I want. That's not increasing speed. So what's happening on the other part? What's happening on the other part of my graph? Well, starting at 3, working my way to the right, I start off at 0, and then my speed is getting larger and larger and larger. If I look at the y value of that graph, it's getting higher and higher and higher. My speed is going up and up and up. In other words, my speed is increasing. So starting at t equals 3, going to t equals 8, my speed is increasing. So I'm going to not include 3 again because the speed was 0 there. So we'll say 3 to 8, my speed was increasing. You can also relate this to an idea in Calculus 2, which I think is kind of neat. Just for those of you who plan on taking it, you'll talk about different types of curves and different ways to graph functions. And one of those types is you might have a parametric equation, which is an equation that depends on time, which means that the curve also has an orientation. And if you think about this, this makes sense for this problem, right? Time only moves in a forward direction, assuming we don't have any sort of time machine here. So if I visualize what's going on here, is if I start positive, end up at 0, well, I'm slowing down over time. What's happening over here, I start off at 0, I kind of rebound, and I go up and up and up. My speed is increasing right here. So we're going to take a look at a few more examples of these, and hopefully by the end of this section, we'll feel a little bit more comfortable with the relationship between position, velocity, speed, and acceleration. That's our goal for this section.